Hello everyone. I'd like to welcome you all to today's webinar, Analysis of Beer, Wine, and Components for Pesticides Using High-Throughput Techniques and QueChERS. I'd like to introduce myself. I'm Amy Williams and I'm the Marketing Manager here at SPEX CertiPrep, and I'll be moderating the presentation for you today. But before we begin, I'd like to get a few housekeeping items out of the way. So everyone that registered for the webinar today will receive emails. The first one will be with the presentation slides, and the second one will be with the webinar recording that's housed on our YouTube channel. And if you have any questions during the presentation, you can just type them into the question box on your screen and we'll answer them at the end of the presentation during our Q&A session. And I also want to let everybody know that we'll be giving away a chemistry spice rack at the end of our presentation, so please stick around for that at the end. So now I'd like to introduce our presenter today, Pat Atkins. Pat is the Product Application Specialist for SPEX CertiPrep, and you'll recognize her as a regular from a number of our past webinars and research projects. So with that, I'll hand it over to Patty.
Thank you very much, and I'd like to welcome everyone to our presentation on beer, wine, and their constituent components using high-throughput techniques and QueChERS. When looking at QueChERS studies, we definitely have a world open to us of what can be studied using the QueChERS method. We have new environmental samples and, of course, our agricultural and traditional samples. So when we were looking for a new project for our QueChERS, we looked to our company and we looked to our previous studies and tried to decide on a product that we could look at that was near and dear to everyone at SPEX CertiPrep's heart. So for our newest study, you may have attended one of our previous webinars on the art and chemistry of wine. We decided that wine and beer would be the perfect opportunity for us to test our high throughput methods for QueChERS. Because as Ben Franklin said, in wine there is wisdom, in beer there is freedom, and in water there is bacteria. When looking at wine and beer and their agricultural products, wine primarily we're looking at the grapes. There are other agricultural products in it like yeast, some preservatives, sugar for some varieties of wine that are fortified, as well as finishing components to clarify the wine. For beer, it's stocked full of agricultural components. You have your grains, your barleys, your hops, your yeast, and your added flavors. Just a little bit of background on wine because it's very interesting and it kind of leads into how pesticides are concentrated in final products and how pesticides would end up in our finished wine and beer. If you look at the winemaking process, you have your grapes which you crush, then you punch down the must. This is the beginning of the fermentation process. You get all of the skins coming up to the top. If you're making red wine, those skins will be kept in contact with the wine for a lot longer. And if you're making a white wine, you would remove those skins so the color and the chemicals in those skins would not react as much with the finished product. You then press your grapes, you cask and ferment your wine. This can be a process that takes several years. Some very fine wines can be in casks for many, many years before they're put into a filtering apparatus or they are fining. They would add chemicals or substances. Some wineries or some wines actually use eggs as a finishing to remove the particles from the wine and filter it. And then finally, it is bottled. Some interesting facts, all of those grapes, you need 10 ounces of grapes to make a 6-ounce glass of wine. That equates to 5 1/4 pounds of grapes to make one 750 ml bottle of wine. So that's a pretty good amount of agricultural product that goes into each bottle. The beer making process is a lot more complicated, or at least it has a lot more small steps to it. You first have your barley, and the barley is treated to a process called malting, where it is steeped in water, it's allowed to germinate, then it's put in an oven or a kiln where it is baked to a nice toasty color. After it has been malted, it is milled and then put into a masher where this grist is mashed, and then it is put, that wort, that liquid is put into the kettle to brew. This is where you would add your hops. And once the kettle has basically cooked your wort, it's put into a separator where it then goes through several fermentation vessels or separators to a maturation tank. It's filtered, and finally your final product gets either placed into a keg or into a bottle for your enjoyment. Compared to the wine and the wine grapes, you need just over a pound of barley to create a 6-pack of beer. What you end up with is chemistry in a glass. You can see that the primary ingredient of both wine and beer is water, and a smaller percentage of that is ethanol. For wine, you're 70 to 90% water and 6 to 23% ethanol. This varies by variety. Things like a table wine or a claret can be about 6 to 8%, up to about 14%, all the way to a fortified wine, which like a port, which would be 20%. Most of the alcohol content in wines is limited to 18% unless you add some additional sucrose to fortify the wine. That would boost the alcohol level past 18%. The vintners would like to keep the alcohol percent above 9% to prevent the introduction of Acetobacter, or the mother of vinegar bacteria. This bacteria, if it invades the wine, will turn the wine to vinegar, especially if that alcohol content isn't kept above that 9%. Most vintners want a wine with about 24 bricks, which equals about 13% alcohol. This is the target for most wines. And of course, there are some differences depending on the varietal, as you can see in the table. For beer, it's about 90% water, and anywhere from about 2 to 16% alcohol on average. Your light beers have very little alcohol with 0 to 3%, and then as you go down the list, you can see like an IPA is about 6 to 7%, with the average amount of alcohol in beers being in that 3 to 6% range. Then you have some more fortified beers. Something like a stout can get up to 10%, and then you can have the super fortified beers. About 3 or 4 years ago, a brewery in Germany announced that they had made a 47% alcohol beer, and then they topped themselves a year or two later by introducing a 57% alcohol beer. But typically, the range for ethanol in beer is between 2 and 16%. Some of the other chemicals that can be found in wine, the good and the bad. For wine, you have pectins, proteins, and acids, vitamins and minerals, and then you have all the flavoring components. These are a very small percentage of the product, but they are very important for the character, the taste, the flavor, and the aroma of the wine. Your polyphenols, your flavonoids, other trace flavor compounds, and then of course you have your potential bad compounds, or your unnecessary compounds as far as flavor and character of the wine, your pesticides. For your beer, it's about 4 to 8% carbohydrates, your hops, barley, and the rest. You have a little less than 2% aroma and flavor compounds depending on the variety and the type of beer and hops that are used. And again, you have your parts per million or parts per billion pesticide levels in your finished product. Most of the flavor from a wine grape actually comes from the outer levels of the grape, the skin and that very first layer, that peripheral zone. This is where you find all those aroma and flavor compounds, things like the tannins and the catechins and resveratrol. All of these are located in the top layer of the skin. And then as you get into the center, it is more the sugars and the organic acids. Here's a little table of some of the more important aroma and flavor chemicals that are in wine varieties. What's very interesting is there's been a lot of research over the last few years trying to really pin down which of these compounds give the particular flavor or notes to a wine or to a beer that give the distinct character of that particular wine. You have things like your methoxypyrazines, which are all of those compounds that give those grassy, peppery, earthy kind of scents and taste. They're very characteristics of a Cabernet Sauvignon or a Sauvignon Blanc. Then you have your thiols. Those are your mercaptans and other compounds. They're the skunky, garlicky odors. Some of them are considered to be characters of a particular wine, but in most cases these things are considered to be faults in wine. They don't want these flavors in it. For ports and other very rich sweet wines, you have your glycosides, which give you those tobacco and chocolate. But a really big field of research recently, and I'll explain in another minute why it's become exploding, this field of research, are these terpenes, these terpenoids. These are historically flavor and aroma compounds. They are in perfumes and they're foods and spices, and they're very rich compounds. And the combination of these compounds with other acids and proteins in the different matrices, whether it be wine, beer, or anything else, contribute to the character and the enjoyment, the aroma, the flavor, and just the overall profile of these products. If we look at a hops, it's kind of simple compared to that wine grape. You have the female flower bud, which is called the bract, and inside you have small looping glands, and in these glands are the organic acids and the flavor and aroma compounds. Now, if you look at the chemistry of these aroma compounds for beer hops, most of it is organic acids like alpha acids and beta acids, and then you have all the terpenes and terpenoids. These are all of the oils and flavor and aroma products that are found in the hops. Now, the alpha acids and the beta acids are bittering compounds. They make that bitter flavor, that hoppy flavor people associate. And it can be anywhere from 2 to 18% of this bittering alpha acids. And craft beers that consider themselves hopmeisters or hop masters, they tend to have these high variety hops like a Warrior or a Tomahawk to really give it that punch. Then you have the more subtle terpenes, which change the flavor and the profile of the hops and therefore the beer. You can have a myrcene, which is grape, peach, vanilla, and it's also like a wine smell. So this will give a citrusy flavor. You get these in the light ales and your Oktoberfest, your wheat beers. And anything like a humulene will give you more of a woodsy, spicy, coriander kind of note to it. And these you would find in bocks and lagers and things like that. So the chemistry of these alpha acids, these beta acids, and these terpenes really give the beer and the wine those notes that we all talk about. So in general, terpenes are organic compounds, aromatic hydrocarbons in fact, and they're units of isoprene. You most commonly find them produced by lots of different varieties of plants. We commonly come into contact with terpenes every day in the form of conifers and pine trees. It's interesting that a lot of pollution research, air pollution research, has been done about terpenes because terpenes contribute to the natural air pollution that we find in the world, and there is natural air pollution. If you think about the Smoky Mountains, or the haze that goes over conifer forests, these are all the terpenes mixed with fine particulate matter that hang over the ground and do create air pollution issues. They're very strong smelling, and if you add a functional group to a terpene, you end up with a terpenoid. For wine and beer, you can see the differences in these aroma compounds. For grapes, you have about 40 terpenoids, and these are the 3 most important terpenes and terpenoids for wine grapes, and they're located in the outer layer of the grape in the skin. And an interesting fact is some vineyards will actually encourage the growth of some fungal compounds because it boosts the ability of the production of these terpenes or terpenoids. It increases the flavor content of the grape. But it's only a fraction of the compounds found in wine and found in these grapes, less than 1%. Now the hops, on the other hand, have hundreds of these terpenes and terpenoids. Here is the list: limonene, linalool, and a bunch of others. They're found in those lupine glands. It's about 1 to 5% of the total compounds that the hops would produce. And the oil from those hops, it can be up to 50% of that oil. Here's a little snapshot. I just kind of wanted to take a look at some of the most common terpenes and terpenoids, and then we're going to get off to another chemical component that we find in the wine and the beer. But these are some of the most common terpenes and terpenoids that most of us have experienced by smelling or using, and if you blend fragrances, these would be very common to you. You have your pines, your pinenes. There are things like your limonene, which is your citrus and lemon, your linalool, which is a mint or lavender kind of smell, your humulene, which is primarily a hops component, your geraniol, which is roses and wine grapes, and your myrcene, which is myrtles and of all things, cannabis. This becomes also very interesting to the new and opening field that is developing in this country with the introduction of cannabis testing in the country as the laws start to change and it starts to become an agricultural product that needs to be monitored and controlled. Finally, we get to our undesirable chemicals in our wine, the things that we don't really want in our wine, but by default, because they are agricultural products that are on our products, are pesticides. Here's a list of several dozen of acceptable pesticides for use on wine grapes and on hops. You can see there are dozens and dozens of them. For wine grapes, the most commonly cited pesticide claims to be oils or pesticide oils. But imidacloprid is claimed to be the second most abundant pesticide applied for wine grapes. And coincidentally, it is the first most or the primary most used pesticide in the world. So it has a very large usage in the world. Over the last year or so, it has been linked to papers citing it as possible beehive collapse. So we've heard of the collapse of honeybees due to possible pesticides. This is one of them that they have linked to that. Also, in our wine and our beer hops, there is carbaryl used, and it is the third most pesticide used in the world. Now, 7 is a very common pesticide in agricultural means, but it's also very common in the home gardening. So this can be purchased through many different sources, and it is used all over the world. For the hops, imidacloprid, carbaryl, and bifenthrin have been cited quite a bit as being used on hops. When we're looking to extract our agricultural products, we have many means open to us. We have our traditional methods of soxhlet and supercritical fluid extraction. We also have our microwave extraction. But every issue has its problem, or every method has its issue. You have your contamination issues, your poor recovery issues. Some of these methods use tremendous amounts of solvent, which creates waste. You also have specialized cartridges and equipment for things like SPEME or SPE. You sometimes also have high volumes of samples that have to be used to do a proper extraction. That's why when QueChERS was introduced, it was one of those clarity moments for most laboratories, because here was something that proposed that it was going to be easy and it was going to be cheap, quick, efficient, rugged, so it would be reproducible in their lab, and the materials were pretty safe. So here QueChERS was born, and it became that aha moment for a lot of labs, like, oh wow, there's an easier way. And the nice thing about it is it increased their laboratory production and their efficiency in their lab. For us, that means it's increased the tempo. We think of this tempo to be a characteristic rate or rhythm or pattern of work, activity, or music. But I like actually the definition in chess better, especially as it applies to the lab. It's the gain or loss of time and effectiveness due to one's mobility or developing position in respect to the number of moves it required to gain an objective or outcome. If you're working in an analytical lab, you're always thinking about your gain of loss of your time or effectiveness. You're always looking on how many steps in an SOP is it going to take to get the best objective, your best extraction, your best recovery. So I kind of like this definition a little bit better. So when we look at tempo and we take a snapshot of an experiment for our tempo, we're looking at how much time does it take, how efficient is the method, what's our cost in manpower and in supplies, how long does it take the process, is this a 5-step process or a 50-step process, and how will that output, how many samples throughput can we get through our lab. If we look at a typical QueChERS experiment, these are all the possible steps you have in a QueChERS experiment. You have your initial sample prep. Now, some laboratories are very lucky and they receive pre-homogenized samples. They don't do really any sample prep. They take their sample and they go on to the next step. Some labs actually get agricultural products in their raw form and have to do some sort of sample treatment or processing or homogenization, grinding on that sample, and that can take a lot of time, a lot of effort, and a lot of money. You weigh your sample, you add your solvent. Now again, you can weigh out all your salts. If you buy your raw materials and you feel that this is something that your lab has the ability to do. You would weigh out all those different salts in your extraction kits or in your extraction method, and you'd weigh them out, you'd add your salts, or you could conversely buy a kit. There are many QueChERS kits available where you would just basically add your sample to it and then go on. Then do you make your own standards? Of course, we at SPEX CertiPrep will hope you buy our standards, but if you do make your own standards, you allow time and money and manpower to make your standards, and you QC them, make sure that they fit your purposes. You make your internal standards and your spikes, and you go on. You shake your samples, you centrifuge them, and then you decant for your second step. All of this comes with a cost, time, energy, and money. In order to go through a typical QueChERS experiment, it's anywhere from 4 to 14 hours to extract 50 samples, and you're spending about $1,300 to $1,500 in materials, depending on what you're making yourself and what you're buying, and you're spending between $400 and $1,400 worth of manpower hours. And this again can change greatly depending on if you have to do that initial sample prep, if you're making your own standards, if you're weighing out all the salts individually, or if you're doing a high throughput where you're buying all these kits put together for you. If you're looking at the second step, the tempo of the second step, or the cost of the second step, is between 2 and probably over 8 hours, depending on how you are going to do that last step of preparing them for QC or preparing them for your GC or LCMS. So your last 6 steps can cost you between $110 and $220 in materials, and anywhere from $200 to $800 worth of manpower hours. So taking a snapshot of what a typical QueChERS experiment looks like, you're talking between 6 and 22 man hours to do this experiment. The cost is going to cost you about $2,000 to $4,000. The process is going to be about 16 steps at 2 to 3 hours a step, and your output will be, depending on how good you are and how much you do this, anywhere from 1 to 4 days for 50 samples. Several years ago, when we were still new to QueChERS and QueChERS was an idea that was still growing instead of being widely accepted as it is now, we decided to do an experiment using apples, strawberries, and green peppers. At that time, we chose to do all of our preparations by hand. So we weighed out all of our salts, we mixed all of our solvents, we prepared all of our samples. We actually had apples and green peppers and strawberries, and we ground them. The only automation that we put into our method was we compared manually shaking those tubes, and we had our Geno grinder from SPEX CertiPrep. So the Geno grinder took over the hand shaking. So we split our samples in half, and we compared the manual versus the Geno grinder. It took us 5 days for 2 scientists, and we were kind of new to this, so we did a little bit of fumbling at first, but it took us 5 days to complete the 50 samples. We found by automating the Geno grinder for our shaking process, we actually improved our efficiency. Our recovery of our pesticides went up about 37%. As far as money, we spent about $4,200 of time and materials to create all of this experiment and run this experiment. It took us the 16 steps because we did do everything by hand, and it was about 2 to 3 hours for each step, and it took us a week to do our 50 samples. So when we decided to do a second experiment for QueChERS, and we wanted to pick our wine and our beer and our grapes, we decided to see how much we could really maximize the throughput, what we could do to speed the process up, and how would that affect our efficiency and output. For our time, we decided to use prepackaged kits. So we have our SPEX QueChERS kits, and we use those. And of course, we used our own prepared standards. SPEX has a line of QueChERS standards. We used our SPEX CertiPrep shaker, which is a smaller version of our Geno grinder, and that would take over the shaking and grinding of our samples. And we purchased a high throughput reactotherm so we could blow down our samples much more quickly. For money, we believed time was money, so by using all these prepackaged materials and some automation, we were saving ourselves laboratory time and speeding up our process. And in the end, we did eliminate 3 of those process steps, which included weighing out all the salts and prepping all the standards. For our samples, we had 2 wine grape samples. We had a Malbec and a Syrah. Now, we got these from an urban vintner. For us, our urban vintner is a place that we go as a company, as SPEX CertiPrep and SPEX Sample Prep. We make our own SPEX branded wine as a management activity. So this urban vintner is where we go to produce our SPEX wine. So we were able to obtain Malbec and Syrah grapes. We had 6 red wine samples from the 2 varieties that matched the wine grapes. These varieties were from South America, the US, Europe, and Australia. And we were looking to scan for any pesticide residue. We wanted to see if the components matched what we would find in the finished product. We also wanted to see really how we could speed up our tempo, how we could improve our process and have a better output. For our beer samples, we had 2 grain samples. We had an organic grain sample and then a traditional or regular non-organic grain sample. We had a dark malt sample. Now if you go back to thinking about that process of making beer, dark malt is the end process where the malt is, or the grain is malted, and it is allowed to germinate, and then it's toasted and ground into a powder. So this was a already malted grain sample. We had 4 beer hop samples, and these are very common hops used in a lot of craft beers here in the U.S. Cascade, Magnum, Centennial, and Citra hops. And we had 6 corresponding beer samples, all from U.S. breweries. These are all craft beers, and they matched the beer hops that we had chosen for this experiment. For our materials, as I said before, we did choose to use our new QueChERS kits. So we used our AOAC QueChERS kits for our extraction and our dispersive. We used the general kit. We used acetonitrile with 10% glacial acetic acid. And then we also, of course, used all of our SPEX CertiPrep QueChERS standards, our AOACIS and our spiking solution, along with CLPS I90, which is a deuterated IS solution we use for our GCMS. Here's a list of all the pesticides in that AOAC spiking solution. You can see there's a wide range of pesticides, 27 of them, and they're at 40 micrograms per mil concentration. When they were spiked into our samples, the outcome of the spike samples turned out to be slightly different amounts depending on the sample type. Now grapes, when they were ground, we put in our spike samples and we were able to get what we predicted, about 1.9 ppm, because we were putting in the 10 mils of acetonitrile and we were getting 10 mils back. For our wine and beer, it was a little bit of a surprise though. We started getting back more acetonitrile phase than we expected, and then it occurred to us, well, these wine and beer have a fairly high amount of an organic solvent themselves. They have the ethanol. So part of that ethanol would partition into the acetonitrile phase, therefore giving us a larger sample volume than when we started. So that changed the amount of spiked AOAC spiking mix in each of these wines and beers a little bit. So they dropped the target from 2 to about 1.3 to 1.5. Now the hops and grains were the inverse of the wine and the beer. They were very dry components and they needed a lot of acetonitrile in order to get enough sample to do further testing. And that dropped it to about 1 ppm. For our equipment, we used our SPEX Sample Prep freezer mill. This is really good for things like seeds and spices and other things like that. It was perfect for grinding our wheat. Using liquid nitrogen, we were able to get a very fine, homogeneous powder, and we were able to get our 10-gram samples. Our sample prep shaker then was used in our QueChERS analysis. We were able to increase pesticide recovery by automating our process of shaking. This eliminated our variation. So we had no variation in how fast or how long a sample was shaken. Anybody who has done the traditional QueChERS method with shaking knows that for the first 6, 10, or 12 samples, you're pretty much going strong, but then every subsequent set of 6 or 10 samples, however many you can hold at a time, you start to slow down because shaking these samples can get very tedious and quite exhausting, especially if you're doing batch after batch after batch. And we did find that there was variation. There was two scientists shaking these samples, and one scientist was shaking them very vigorously every time, another one was kind of slowly going back and forth with them. So we decided that we were going to compare again this manual method by having some of them manually shaken, and then we were also going to use the shaker to see what the improvement would be by doing this automated shaking process. We did add grinding media. We added ceramic grinding media to both the manual and the automated shaking method, because in the past we found by using these ceramic media you actually do improve your recovery overall. We also had our typical centrifuge that was able to accommodate our 50 mil and our 15 mil tubes. And as I said before, we did purchase a higher throughput reactotherm which could do dozens of samples at the same time. In the reactotherm we exchanged the solvent to dichloromethane and we concentrated the samples down to 1 mil. The samples were run on our Agilent GCMS using a DB5 equivalent column and in scan mode. Many laboratories, when they choose to do pesticide analysis, will do a sim mode method, but we were really curious to see what we would see in scan mode. We always like to keep it in scan mode just to take a really good look at everything that's in a particular sample. But the trade-off of that is you lose some of your sensitivity and you lose your ability to basically sort out some of the larger component compounds from some of the very small pesticides. We did have a few challenges when looking at our pesticide response. Some of the pesticides were destroyed or captured using the process. We had almost no recovery of the chlorothalonil and the thiabenzidol. We also had lowered response of some of the pesticides like the trifluralin. We also found that some compounds actually interfered significantly with detecting some pesticides. In particular, an N-hexadenoic acid was coming out over at the same time as the linuron. So this is a fatty acid, and it was found in the wine, the yeast, and the beer. And we believe it's part of the yeast that is used in wine and in beer making. We also had a few compounds that gave us a pause or two that we had to take a deeper look at. At first we thought we had a follicule peak, but then looking really closely at it, we decided that it was a misidentification. It was actually a diketopiperazine compound. Doing a little bit more research about it, we found that it is a bittering compound, and it wasn't found in our wine or our wine grapes or our grains, but it was found in our beer and our hops. This further led us to believe that this is one of those aroma and flavor compounds that are associated with the beer and the hops. We did also see in our wine and our beer a very high peak for carbaryl, seen much higher than what we spiked into our standard. When we looked closely at it, it actually was identified as 1-naphthol, and we were a little disappointed at first because we expected it to be carbaryl. Then we did more research into it, and we found that the 1-naphthol is actually a breakdown peak to the carbaryl. And we did see it highest in the wine and then in the beer, but we did not really see it to a high extent in any of our solid materials. Looking at our wine and grapes, there was primarily one compound or one pesticide that we found in our wine grapes. It was the imidacloprid at about 1 ppm. And in this case, we only saw it in the samples that we used the automated shaker for. We did not see the imidacloprid at all in samples that were handshaken. In our wines, we did see a variety of different pesticides. The most dominant pesticides were carbaryl at about 3.7 ppm, found in most of our wines, and the imidacloprid at about 2.8 ppm, also in most of our wines. Then we saw a variety of different pesticides in 1 to 2 of the wines, the ethion, the bifenthrin, and so on. One of the surprising things that we found was we did not expect to find an increase by using the shaker on a liquid product. We really believed it was liquid. The hand shaking versus mechanical shaking would not really make a big difference, but that actually was not the case. We did find a higher recovery in our wines, up to about 15%, by actually using an automated process of shaking. If we look at the wine and the wine grapes, you can see that the imidacloprid was found both in the grapes at 1 ppm and at the wine at about 2.5. For the wine, we also did see in addition carbaryl, lambda cyhalothrin, and endosulfan sulfate. Now turning to our beer, we'll start with our grains and our malts. First, if you look at the barley, we did not see that bittering agent. That piperazine compound was not in these malt or grain products. Looking at the organic versus the regular grain, we did see an increase in the regular grain compared to the organic grain. So something like a bifenthrin, we did see at about half a ppm in both, but in ethion, we had 3.6 ppm in the regular grain and about 1.4 ppm in the organic grain. So there was less pesticides found in the organic grain. For recovery, by using an automated shaking method, we got between 10 and 25% higher recovery using this shaker. For our malt, primarily we saw imidacloprid was the largest pesticide found, and it was at a fairly low level, about 0.75 ppm. We also saw less than half a ppm of bifenthrin and endosulfan sulfate. Now there was a study that was done in the last few years that was tracking the pesticide levels in barley before and after it's been malted, and they did show a decrease in pesticide levels from the barley stage to the malt stage. By far, one of the most interesting compounds or constituents we looked at was the hops. It was full of all the different compounds. We did see that bittering agent up to about 18 ppm. And in order to see pesticides, we would really need to go further in our cleanup. We would need to add some of the other dispersives, the C18 and the carbon black, to really clean up a lot more of this material, because there were some very large organic compounds, including vitamin E, some phytosterols, and of course those interesting flavor and aroma compounds, the terpenes. In particular, very pronounced were beta-pinene, the caryophyllene, the alpha-humulene, and the lupulon. Now these particular really large organic compounds did interfere and coalute with some of the compounds of interest that we were trying to see, the imidacloprid, the ethion, the bifenthrin, and the endosulfan sulfate that was seen in some of our other beer components. But just a little side note, because we said before that the up-and-coming wave of the future is going to be cannabis research. When I was looking at some of these terpene compounds in the hops, I started to be reminded of some questions we've been getting lately about terpenes in cannabis. Well, there's a good reason why these compounds seem so familiar, because both cannabis and hops are from the same botanical family. And they both have between 100 and 200 terpenes or terpenoids. So there are very many of these terpenes that are common as aroma or flavoring components to hops and to cannabis. And just so you can get a little idea of how these fall, if you look, here's a chart of some of these common terpenes and where you would find them. So quite a few of the terpenes, the myrcene, the limonene, the linalool, are common amongst wine, hops, and cannabis. So there's a lot of similarities on these very strong flavor aroma profiles for these three agricultural products. When we look at the pesticide levels in the hops, we saw the most pesticides in the hop products of any of the other constituent components, or even as of the finished products. We saw ethion from 1.6 to 9 ppm in most hop varieties. So you can see that the ethion was found in 3 out of 4 of our hops varieties. There was also a substantial amount of imidacloprid in 2 of our varieties, and carbaryl was found also in 2 of our varieties. What was very interesting is that the pesticide profile for each of the hops was different, so we didn't have duplication of the same pesticide profile for each one of the hops. Finally, in our finished product, our beer, again, we did see that bittering agent. We did also see the same pesticides we found in our hops in our beer. The imidacloprid was at a lower level at about 5.25 ppm, the carbaryl at about 3 ppm, and the ethion at about 2.5 ppm. Again, with what we found with the wine was surprising, that with the beer we were able to increase our recovery using the shaker versus a hand shaking method up to 35%. You can see that we really did increase our recovery, something like a chlorpyrifos, where we had a fairly low recovery with hand shaking, but with an automatic shaker method we got basically full recovery with it. If we compare our beer, hops, and grains, we did see that bittering compound in just the beer and the hop samples, so that would be consistent with what we would expect. We were able to increase our recovery up to 35% using our shaker. So the manual shaking method, while effective for many compounds, can be improved upon by automating the method. We did find pesticide in almost all of our beer and wine components, and we primarily saw things like the imidacloprid, the ethion, and the bifenthrin. Now, it's possible that there was bifenthrin also found in the hops, but the interference of some of those larger organic compounds did take away from our ability to see if that was a contributing factor to the beer. If you look at the different components of the beer, the malt, you can see that the imidacloprid was the most significant pesticide we found. For the organic grain, it was ethion, and the organic grain and the regular grain, it was ethion. For the hops, we did see the imidacloprid and the ethion. And then if you look at the beer, you can basically see that all of those components that are represented in different amounts in the beer. Here are some of the smaller pesticides that we saw. Again, you can see the malt, it was the endosulfan sulfate, within you do see in the beer. The grain and the hops, you see that carbaryl, which did contribute overall in the finished product, and then the chlorpyrifos methyl as well. A final snapshot at our tempo. How did we do when it came to looking at our final process and output? It took us 2 days to do all 50 samples. There were 2 of us, and it was an easy 2 days. It wasn't like a rush 2 days that we're trying to get everything done. It was a fairly comfortable pace. Our efficiency, our shaker actually increased our recovery anywhere from 5 to 35%, so it did make a difference on how well we recovered our pesticides. As far as money went, we were decreasing our manpower hours, so we did save ourselves money in that case. And our kits and our standards were all prepackaged. Again, no buying of large raw materials, so we did save some there. Overall, from our initial experiment where we spent about $4,200, this time we spent about $1,800, and we saved ourselves $2,400. Again, we eliminated 3 steps, reduced our amount of time of each step by about an hour, and 50 samples were produced in 2 days. If we look at our pesticide snapshot, our wine and our grapes had fairly low levels of pesticides. The wines had under 3.5 ppm max, with carbaryl being the largest pesticide. Our grapes had under 1 ppm, with imidacloprid being the largest. For our beer, grain, and malts, the beer was about 5.25 ppm most, with imidacloprid topping the list, but most of the other pesticides were below the 1.5 ppm level. Our grains and malts contributed very little to the pesticides that we were looking at under 1.5 ppm. And our organic grain did have a lot less pesticide residue than our regular grain. Of all the components, hops was the highest of all the products we looked at as far as pesticide residue, ranging in the high of 7 to 9 ppm for things like ethion, imidacloprid, and carbaryl. And definitely the most prolific pesticides we did see were the imidacloprid and the carbaryl. Overall, we improved our time, our efficiency, we saved some money, we improved our process, and we definitely had a better output for our QueChERS, second QueChERS experiment. So what's in the future for QueChERS? QueChERS is being used a lot for some non-traditional samples. We've been asked in the past year a lot about applications for using QueChERS for environmental samples like soils. We've also been asked, can you test for phthalates using QueChERS? Vet residues are on the rise being tested by QueChERS, and untraditional matrices. So what's next for QueChERS? Obviously, this new world that's opening up of cannabis testing, these previously untested for agricultural products, is on the horizon for what will be new in the future for QueChERS, and whether QueChERS and the cannabis testing will be a good fit. So what's next for SPEX CertiPrep? I know sometimes we get asked, well, what's going to be your next project? Well, we've listened to your feedback, and we've actually had a lot of inquiries about if we were going to do spices. So for our next project, we will be looking at some of the heavy metals in spices, and you are invited to join us at PitCon, where we will be presenting about our spices, heavy metals and spices.
All right, thanks very much, Pat. That was a lot of good information, and we have a few questions that we wanted to address before we finished up here. So I have a couple questions for Patty. Pat, did you test any beers from outside the U.S., from any other countries?
No, we actually only chose the craft beers here from the U.S., and this was mostly done because some of the craft beer companies are very public about the different blends of aroma compounds or hops for those aroma compounds. So we were able to find a lot of data on what the types of hops that these different craft breweries were using to produce these beers. So it made it easier for us to match these craft beers here in the U.S. with the different hops that were being sold here within the U.S. So that's why we chose these small craft breweries.
Okay, another question we received, did you try looking at the hops after using a different QueChERS DSPE?
We have not looked at the hops again using a carbon black or a C18 product. This was a one-time experiment, although we have had some requests to see if we could further clean up the hops, especially because of the relationship with cannabis. So there has been some request for us to follow up a little bit and see if we could target these specific compounds, whether it be the cleaning up for the pesticides or trying to target some of these aroma and flavor compounds in things like hops and in the cannabis.
Did you test any name brand commercial beers?
We specifically chose not to test some of the bigger beer brands that Americans associate with beer drinking for several reasons. First of all, they're not always very open to their formulations and what types of hops and other constituent products they're putting in their beer. Secondly, a lot of major brands, ones that you would see in your supermarket or your liquor store, would supplement their barley content with other grains, things such as rice. And we really wanted to particularly focus on that one type of grain and not go into 5 or 6 different grain products. So we tried to stick with small products, small craft breweries, or breweries that were very open about the composition of their beers.
Okay, and I think we have time for just one more question. Do you think that QueChERS will be the best method for extracting pesticides in cannabis?
Well, as I've said before, this is a new field, and we are now in the midst of having government officials start to compile lists of which pesticides are going to be allowed, at what levels, and how they'll be tested for. There's going to be a lot of growth in the next few years and next few months about how best to do this type of testing. Now, that's all going to come down to how the laboratories are allowed to test. How sample limited will they be, since this is going to be an agricultural product with some value to it? Is there going to be a question on being sample limited or not? And if so, then QueChERS may or may not be the right choice, because QueChERS does require 10 or 15 grams of sample in order to get a good extraction and to be able to test by GCMS or LCMS. So because QueChERS has been modified so many times, there might be a modification in the works in order to kind of get around this and make it a viable solution for this. So I think time is going to tell. I know here at SPEX that's a question we've been pondering quite a bit, and we'll be doing a little bit of reconnaissance and R&D on our own to see how this QueChERS process might fit into this brave new world that we're all entering in this new agricultural product that's opened up to the analytical world.
Okay, thank you very much, Pat. I want to thank all the participants for attending the webinar today, and we look forward to seeing you at our future webinars. Thanks so much.